So in the last live session, we started we continued our discussion on micromechanics of composite, wherein we summarized all the relationships as shown in the table. Okay. Knowing the properties of fiber and matrix and relative proportions, we saw how different elastic properties can be computed, and we emphasized on the importance of rule of mixtures. Then we saw a couple of numerical to understand the application of these relationships also. Then we started the discussion of manufacturing methods of FRP. In this, we talked about three major categories: contact molding, compression molding, and filament winding. Okay. So in contact molding method, we saw hand layup method and spray up method. In these, FRP are manufactured using open-ended molds. Fiber layer are placed and then matrix is added either by brush or pour or using spray. In compression molding method, we saw match die molding. Okay. Forming method employing gas pressure, closed mold molding employing low pressure, and pultrusion forming. Okay, the basic behind all these were pressing and squeezing a deformable material between two halves of a heated mold or a feed material, and its subsequent transformation into the molded part after cooling and curing. Okay, the most advanced among these were pultrusion molding, where instead of compression, fibers after passing through matrix bath are pulled and cut into desired shape. Okay, and last was filament winding method, which is a continuous process that offers self automation. Here fibers are made to pass through a resin bath and collected over a rotating mantle. After this, we talked about application of FRP in strengthening and retrofitting work. Why FRP is preferred over concrete and steel? Due to its corrosion resistance ability, lightweight, high strength to weight ratio, high strength and stiffness, durability, and easy fabrications. Okay, we saw a few example how FRP is used in structural strengthening. Then we dug deep into into the application of FRP for different strengthening requirement. We first talked about flexural strengthening, then we talked about shear strengthening, and then axial strengthening. For each of them, we talked how FRP causes strengthening, what are different factors that affect the strengthening by FRP, what are the different ways in which failures can occur when we strengthen a structure by FRP, and then also we also saw several research articles demonstrating the application of FRPs. So this was all of what we saw in the last week. Okay. Now let's see another way in which FRP can be used in strengthening of existing infrastructure, that is near surface mounting. Okay. So near surface mounting can be used for both flexural and shear strengthening of an existing structure. The technique the technique was commonly used with steel reinforcement that we saw in previous lectures. However, it is now finding application with FRP reinforcement also. So, how this near surface mounting is executed? So, first a shallow groove is made into the concrete cover. Then FRP bars are installed into those groove. FRP bars or strips or plates are installed into those grooves, and the grooves are then filled with a suitable grout material. The same process of how we saw in the steel reinforcement when we talked about near surface mounting. Okay, and how this near surface mounting does strengthening. So the technique follows the same principle as a reinforced concrete member. So suppose if we take a reinforced concrete assembly having a NSM strengthening employed near the surface, so under the action of load, this assembly can be broken down into two components. The first component is a simple reinforced concrete without NSM, and the second component is the NSM part. Okay, so this first part, it will take care about of the original load that was acting on the structure, and this second additional part, it will take care of the additional load that is coming on the structure, or for which we need to strengthen the structure. So what NSM does, it helps us to make the choice and addition of NSM for the required strengthening. Okay. So a typical NSM assembly can be categorized into three types. So there can be FRP strip that is grooved near the surface. There can be a FRP plate or a rectangular or square bar kind of thing that we can use, or we can use a FRP round bar, kind of a rebar that we can use. Okay, so these are three categories in which NSM FRP strengthening can be done. First is a strip or a plate, second is a rectangular bar, and third is a circular bar. So from this we can see several benefits of opting for FRP for strengthening. What are these benefits? So since these are mounted near the surface, they require less site installation work. Since they are embedded inside the concrete and not attached on the surface of concrete, they are less prone to debonding failures. Okay, they offer better aesthetics since there is nothing coming out of the surface of concrete, so we can install the NSM bar and we can groove it and it will appear as a part of the structure only and not as something attached on the structure. So it will improve the aesthetics. Pre-stretching can be done very easily in these cases if needed, and they are more durable since they are covered from outside. So they don't offer any durability concerns. Okay. Now, how performance of FRP can be influenced by several factors. Okay, though it offers several advantages, still its performance can be influenced by several factors. What are those factors? The choice of NSM material, whether we are opting for glass reinforced fiber composite or carbon fiber reinforced composite. The shape of FRP, plate, strip, or rebar. Each shape will offer its own advantage. Okay, the surface texture of FRP, whether it is smooth or rough, it will decide the bond between the FRP and the substrate. And the most important among this is the bond behavior between NSM and the substrate, that is our concrete. So the bond between NSM and substrate is important here. Why? Because it will dictate both the load transfer between the two component and the failure pattern also. How? Let's see one by one. Okay. So the bond between NSM bar and the surrounding epoxy or a groove material, as well as between the NSM assembly and the substrate concrete, play a significant role in providing the required strength to the NSM strengthening process. Why? Because it directly influences the failure mechanism of system. Either the failure can occur at the bar epoxy interface or at the epoxy concrete interface. So in the image, we can see all possible failure patterns. The one enclosed in the red box. Okay, these are the failure pattern at the epoxy concrete interface, or yeah, at the interface. Okay, either bar epoxy or epoxy concrete. Okay, so you can see here at the interface of the FRP and the epoxy surrounding it, there can be two types of failure: interface failure and cohesive shear failure. The same kind of failure can occur at the NSM assembly hole, FRP plus epoxy. So this hole is the NSM assembly. Okay, so at NSM assembly in concrete interface also there can be interface failure and the cohesive shear failure. Okay, failure generally occurs when there is the bond between the surrounding material and the substrate is not very good. Then the interface failure can occur, and cohesive shear failure occurs when the bond is weak. Okay, here when there is no bond or there is like less strength, and here when there is the a kind of force is acting which is shearing the bond, then the cohesive shear failure can happen. Okay, while apart from, so these are basically four types of interface area. Apart from this, there can be other possible failure modes also. These include failure of epoxy material itself, that is the grooving material, or concrete failure of substrate. So these are included in the blue dotted box. So here you can see the epoxy material field. Okay, here you can see there was both failure of epoxy material also and the substrate also. Here you can see there was the failure of only concrete. Okay, and here you can see shear failure that happened from the edge of the NSM assembly. So these come under the category of failure of grooving material and failure of substrate. Another common failures that we know already, that is the FRP rupture, concrete crushing, and steel yielding. Okay, so these all we know, that these are very common. So let's see some literatures now that investigated different factors affecting strengthening of NSM. So this was first literature that was published in 2025, an article published in 2025. So their aim was to demonstrate the flexural strengthening using NSM, and the specimens that they used were externally bonded CFRP strips and sheets, and CFRP NSM rods and strips. So they compared both externally bonded FRPs and NSM FRP. Okay, so here you can see in this table the uh, properties of CRP strip, sheet, and rod is given, the thickness, tensile strength, modulus of elasticity, and failure strain. Okay, and this is the testing assembly. So there was a simply supported beam. Load was acting at 2 points, and this was the assembly. Okay, and this diagram shows different samples that were prepared for the particular loading condition. So first was my control sample, which didn't had any FRP. Second was my externally bonded FRP sample. So you can see here externally bonded FRP is attached. Okay, here you can see again one more FRP strip sheet is attached. Here there was a strip, here is a there is a sheet. Here you can see an NSM plate is used, okay, as FRP. Here you can see NSM rod is used with a certain grooving material, and here again you can see NSM plate is used. Now, what is unique between these two? Okay, so here there was anchorage also that was provided. Okay, so if you see from the bottom, so this will be my bottom part. Okay, this is my NSM assembly, and these are additional grooves that were made perpendicular to the NSM assembly and were grouted just to improve the bond between the NSM and the substrate. Okay, now once the load was applied, the ultimate load and shear at strain at ultimate failure were recorded, and it was observed that this fifth assembly, the rod, this one, okay, where FCFRP rod was used along with Anchorage, it led to maximum increase in the ultimate load by 89%. So here in the control sample, it was taking maximum load of 56.91, while in this rod MI20 sample, the maximum load that it was able to take was 106.20. So you can see how much increase in the maximum load capacity happened due to the use of NSM strengthening. Okay, and in what mode it failed? It is D, that is the rupture of NSM FRP reinforcement. So this shows that the whole assembly was used like up till its maximum limit. Okay, you can see the A type of failure, it denotes the steel yielding followed by crushing. So this occurred mainly in the control sample where there was no NSM. Debonding types of failure occurred in B and C category, which are all other categories where sheet was used, external sheet, and internal NSM was used without any anchorage. So in these cases, there was debonding failure that was observed, while the one which had anchorage, it was observed to fail by rupture of the FRP material itself. And the rupture of FRP is the ultimate form of failure. Okay, so we were able to reach the ultimate limit of the use of FRP using this. Okay. In these diagram, you can see how load versus displacement was varying. So this was the response for beam with externally bonded FRP. Okay, so you can see as compared to control sample, it was able to take more load and it was deflecting less when I was using externally bonding FRP. This was with NSM FRP. Again, it was taking more load and deflecting less. This was with NSM FRP without with and without mechanical interlocking, that is anchorage. So here you can see with mechanical interlocking, it was able to take higher load and it was deflecting a little more before failure. Compared to the NSM assembly without mechanical interlocking, it was not taking as much load as the mechanical interlocking one, and it was giving a lower deflection before failure also. So with Anchorage or with the mechanical interlocking, we were able to increase the load carrying capacity also, and it was giving more significant deflection also before failing. Okay, and this fourth diagram is the response of beam with FRP strip without and with mechanical interlocking. So again, you can see the same behavior with the rod one. So with the mechanical interlocking, both load and deflection were increasing. Okay, so it was able to take more load also, and it was deflecting more also before failure. Okay, and now this is the one second article which was published in 2013. It was a review article basically on NSM FRP with and without pre-stressing now. So, what was the aim of this article? Okay, what this article did, so they said that the FRP strengthening reinforcement and interlocking reinforcing steel work together directly from zero loading, leading to higher concrete cracking loads. Okay, uh, so in addition, yielding of steel will occur at a higher load. Okay, when we use FRP NSM, ductility, that's the ratio between the deflection and ultimate load to deflection at yield point of the pre-stressed strengthened beam will decrease as compared to non-pre-stressed strengthened beam, since a portion of strength or strain capacity is already used in pre-stressing. So this says that when we are doing pre-stressing, the ductility at failure will decrease. Why? Because some form of strain capacity of the FRP is already been used in pre-stressing. So it won't give me a higher strain before failure. As the level of pre-stressing force increases, the load carrying capacity may or may not increase while the ductility will decrease. Okay, so you can see in this diagram also, this was A case without any strengthening. This was B case with CFRP NSM rod which was used as strengthening, and C case was CFRP NSM rod used for strengthening, and this rod was pre-stressed also. So you can see significant increase in load carrying capacity happened when we used NSM FRP. Okay, however, when we used pre-stressed NSM FRP, the load carrying capacity increased further, though the strain limit at failure decreased. Okay, and you can see here in the second diagram, as the pre-stressing level is increasing, the load carrying capacity increases up to a certain limit only, but the strain level continues to decrease. Why? Because that strain has is now involved in the pre-stressing. So the more the strain we are involving in the pre-stressing, the less strain it will show till failure. Okay, so this was all about NSM FRP strengthening. Now, FRP also finds critical application in beam column joint strengthening. How? So, beam column joint plays a critical role in stability and performance of a RC structure, majorly in the area which is prone to earthquake activity. They ensure that proper load transfer occurs between beam and column and becomes a critical part of a structure during seismic events where lateral forces are needed to be resisted. Okay, so commonly known reason behind failure of these joints are inadequate design and detailing. That's why we have a separate code, IS code, for design and detailing of beam column joints, especially in seismic prone areas. Okay, so what beam column joint strengthening does, it enhances the shear and the moment capacity, so the joint are capable to withstand more load, and they improve the ductility so that joints are capable to withstand cyclic loading during earthquake activities. Okay, so this is the role of strengthening in beam column joint. And how FRP can be used for strengthening, either as a complete partial or intermediate wrapping material on the beam column joint, and for this we can use either FRP sheets, strips, or plate. Okay, so the ability of FRP to strengthen the beam column joint again can be affected by several factors: the type of FRP used, the amount of FRP used, wrapping pattern of FRP that we used at the joint, reinforcement detailing of joint, and type and extent of cyclic loading. Okay, so let's see some literature on this also, so that we can understand how different factors affect the strengthening of beam column joint, and how we can quantify the factors, how they affect, how they are improvised by FRP, and how we quantify those things, that also we will understand it. Okay, so this was the first article that was published in 2003. So they investigated a mountain wrapping pattern of FRP. So here you can see this was the geometry. So they considered a beam column joint. So these were beam and this was the column. And for this joint, they considered how FRP strengthening will work. So here you can see in this diagram the detail of original reinforcement. So this was on longitudinal reinforcement in the column. These are lateral ties in the column. These are longitudinal reinforcement of the beams, and these are stirrups in the beams. Okay. Now, a total of 18 RC joints were constructed and tested in the study. All the specimens were reinforced such that they would represent a poorly detailed exterior T joint. Why purely detailed? So that we can see failure earlier and we can see how that failure is improvised by use of FRP. So mainly in the testing, they used main reinforcement of 14 mm dia and 8 mm dia stirrups for making the T joint RC. 16 out of 18 sample had no stirrup in the joint, while the two remaining sample had only one column stirrup in the joint. Okay, and the critical point to emphasize in all the specimen were designed such that the failure would occur due to shear in the joint only. So their main focus was shear failure at the joint. Okay. So what are the different specimen that they use? So they designated different specimen by different names. So C1 and C2 were the control specimen without FRP. S33 had three carbon strips on each side for beam and column. So you can see in the second image, three strips for beam, three strips for column were used for FRP strengthening. S63 had six carbon strips on each side of beam and three on each side of column. So you can see in this image, six carbon strips on beam on both the side and three for columns. Okay. S33L was same as S33, but an L-shaped mechanical anchor was also provided at the end of the beam. So this was the S33L geometry. F11 had one layer of carbon fiber flexible sheet on each side of the column and one layer of U-shaped sheet on beam. Okay, so this is my F11. So here instead of carbon strips they use sheet. Okay, F22 was identical to F11, but they had two layers of sheet on both beams and columns. F21 had two layers of sheet on beam and one layer of sheet on column. F12 one layer of sheet on beam and two layer of sheets on column. F22A was identical as F22, but here the axial force that was executed on the column was higher, 115 kilonewton rather than 46 kilonewton that was used in all other samples. There was a sample named F22W also, which was similar to F22, but their anchorage was also provided at short distance away from the joint. Okay. GL is the only specimen which used glass fiber for strengthening. Okay, till now we saw all the carbon fiber strengthening. Here, glass fiber was used. SC was a control specimen with one stirrup at joint. TC was the control specimen with one transverse beam. TF53 had three layers of carbon fiber sheets on one side of column and L-shaped jacket over beam. Okay, so you can see here, this is the T50 TF33 category, and TF22S2 was similar to TF53 plus two strips on the interior side of the beam. So this is the final image. Here you can see there was sheet, carbon fiber sheet and two beams on the interior side of the beam also that was provided. So this was all the samples that they tested, evaluated. Why I am explaining each of them so that you get clarity like how many variables they considered. They use strips, they use plates, they use different materials, different amount of FRP reinforcement also. So they covered almost all types of variation that can cause the strength, that can cause changes in the strengthening of a beam column joint using FRP. Okay, once the sample were prepared, the main part is the testing. How testing can be conducted from beam column joint. So in this image, you can see the schematic of the testing setup. So this is my column. Okay, this is my beam and this is my column. The horizontal part is my column now, and the vertical part is the beam here. So the testing began by slowly loading a applying load to the axial loading of the column by stretching the two high strength steel rod placed outside the column using a hydraulic jack. So what they did first, using like steel rod, they applied the axial load on the column. Okay, once the full axial load has been applied, okay, once this column part was under full axial load, what was this full axial load? 46 kilonewton. Okay, so this maximum load they applied on column. Okay, once this load was applied, they induced earthquake lateral load, which was simulated by applying alternate forces on at the end of the beam using this hydraulic actuator. So using this, the beam was like moved alternately in the left and right direction to apply earthquake lateral load. And the data of the deflection of the beam was collected using the load cell and the actuator displacement. They were recorded using computer controlled data acquisition system. So this diagram shows like how the displacement was provided for simulating seismic activities. And this figure you know now. Okay. So first on the column axial load was applied till maximum limit, and then on the beam seismic load was applied. Okay. So for different specimen, okay, how much maximum load it was able to take in push and pull, that was recorded. Okay, so you can see the F22A and F22W, they were able to take the maximum load. Okay, so you saw what were these assembly, F22 and F22W, they were the assembly where sheet was used. Okay, so you can see here F22W was identical to F22, but they had a improved, their sheet was used and they had Anchorage also. So you can see sheets were performing better than the rods and Anchorage was enhancing the performance. Okay. And how they justified these value, how they obtained the result by from the data acquisition system. So basically the results that they obtain of load versus displacement is in the form of a hysteresis loop. Okay, this hysteresis loop are used to characterize the substantial pitching, which is a typical form of joint failure. Okay, and the failure results in diagonal cracking. So, how to understand this loop? So, initially there is no stiffness degradation. So, initially when applying load, okay, like pull and push direction on the beam, initially there is no stiffness degradation, so my load versus stiffness plot is linear. Okay, now as the number of loading cycle is increasing, the cracks appear in the beam portion. Now due to yielding of steel reinforcement, what will happen, it won't be able to take further load, and post this my FRP will start taking load. Okay, so once the steel has yielded, my reinforced concrete won't be able to take further load. So at this moment, FRP comes into action. Okay, so along after after yielding, what happens? There is stiffness degradation. So due to stiffness degradation, the linearity of plot that was there initially, it is lost, and thus we observe hysteresis loop on cyclic loading. So initially there was a linear behavior. Once there is stiffness degradation, what will happen? It won't be a linear, it won't show a linear behavior anymore, and slowly the load carrying capacity will decrease, and we obtain a hysteresis load. Okay. Now, ability of a structure to resist seismic load depends upon its ability to release the input energy, and this can be done by hysteresis damping. So, larger the area of hysteresis loop, more is the hysteresis damping, and more is the ability of a structure to resist the seismic load. Okay. Due to FRP, the maximum load and hysteresis damping both are increased, as you can see in the figure. In F22, you can see the maximum load that it was able to take was increasing compared to other categories. Okay. So you can see in control, the maximum load was up to 30 kilonewton only, while using FRP, it increased up to 50 kilonewton. And one more thing, you can see the area under the hysteresis loop also increased compared to control sample. Thus, it shows that it was able to take more seismic load. Okay. In these two diagram also, you can see how seismic damping is occurring. So as the number of loading cycle is increasing, the seismic damping is observed in all the members, and the total energy dissipated, you can see in F22, maximum energy was dissipated with the increasing displacement. More is the dissipation of energy, more is the ability of a structure to take seismic load. Okay, So this was one more literature that was published in 2005. Again, they investigated wrapping pattern and amount of FRP. So they used four cases: FRP overlay, FRP overlay with the FRP wrap also, FRP sheet, and FRP sheet and CFRP wrap both in combined. So this was type A, where they used a composite overlay, and this was type B, where they used a carbon plate also. For each of them, loading was applied. Okay, so here you can see my beam column joint completely wrapped with FRP. So this is my column. Okay, under axial loading, and this is my beam, which is taking a seismic loading. Okay, and for this, using load cells and displacement gauges, the displacement and load was recorded, and you can see these are the hysteresis loop. So from these loop, you can see with the use of FRP, the maximum load carrying capacity has been increasing significantly, while the area under hysteresis is also observed to increase. And the maximum increase happened in the sample CP1D. Okay, they here the yielding load increased the maximum compared to control sample, and deflection was also maximum compared to control sample. So what was this CP1D sample? This was, I guess, this sample, the D1, where CFRP wrapping was also done and the carbon plate was also used. Okay. And in this diagram, they showed how the load versus displacement curve was varying. So in CP1, it was able to take maximum load. All FRP reinforced specimen had a higher peak load compared to control specimen. CP1 showed the highest peak load, followed by CL2L, G2L, and G1L specimen. This was the specimen where slope versus displacement. Okay, load versus displacement basically. So all FRP reinforced had a total loss in stiffness at higher displacement than control sample. Okay, so this was observed in all the samples. This is highly desirable phenomena. Why? Because the joint collapse can be deferred through FRP reinforcement like this. And this is an energy dissipation versus displacement curve. So you can see it follows all the sensor closely follows the control specimen. Dissipation of energy is mainly through yielding of steel. Okay, it may be remembered that the FRP remains elastic until failure. Okay, therefore, not much dissipation of energy is expected from the deformation of FRP. However, FRPs have increased the ultimate deformation of the structure to a larger extent. So, this was their observation that they draw from the study. Any doubt in these two parts, beam column strengthening and NSM strengthening? Any doubts in these two parts? If no doubts, we will move ahead. Now we have talked a lot about different types of strengthening like axial, flexure, shear strengthening, NSM strengthening, beam column joint strengthening, and we have often seen in literature while discussing the strengthening of various elements using FRP that the failure is often due to debonding. Okay. Now, such failure is not desirable. Why? Because they are causing underutilization of FRP. Okay. I don't want that my FRP is not failing, but the bond between FRP and concrete is failing. If the bond is failing, what it shows that my FRP is not completely utilized till now. It would have given me more strength if the bond would have been better. Okay. Thus, to improve the efficiency of FRP strengthening, Anchorage systems are used. So, these Anchorage system is a technique for improving the efficiency of FRP strengthening. Why is Anchorage needed? So that the externally bonded FRP system commonly fails. The externally bonded FRV system commonly fails due to debonding at the interface. We want to reduce these. So for this, we need Anchorage system, and Anchorage reduces the debonding type of failure in the FRP. And what Anchorage does, it provides a ductile failure mode instead of debonding failure. So instead of failure of due to debonding, it will provide ductile failure mode either due to yielding of steel or yielding of FRP. Okay, it enhances that stress transfer between the substrate and FRP material where applicable, there where application has geometric constraint. Okay, so all in all, we can say Anchorage limits the underutilization of FRP system, and we saw in couple of literatures today also how with the system which had FRP with Anchorage, it gave the maximum increase in load. Why? Because the failure there was due to ductile failure of FRP instead of bond failure. Okay. Now, when I talk about debonding, there are various ways in which FRP debonding failure can occur. Okay, these are classified into four modes in the present slides. Okay, what are these modes, when and how they occur? Let's see one by one. So my first mode is cut-off cross-section debonding. So they occur when the FRP sheets detaches from the concrete substrate at the end of the plate. So suppose this is my concrete substrate, okay, and this is my FRP sheet that was attached on the on the plate. So if my failure is occurring at this end, then we say it is a cut-off cross-sectional debonding failure. It often results from stress concentration near the termination of FRP material. So such failure occurs due to stress concentration at this location. Okay. Second mode of failure is debonding by flexural cracks. Okay. Here debonding is initiated at the flexural cracks in the concrete. So the presence of crack weakens in the substrate, weakens the bond between the FRP and the concrete material. Okay, so some kind of flexural crack, if they are going, they can cause the debonding between FRP and substrate. Third failure is due to diagonal shear cracks. Okay, so diagonal shear cracks in the concrete can lead to debonding of FRP. These cracks create stress concentration, making interface susceptible for separation. Okay, so due to shear stress concentration due to diagonal cracks, again interface may become critical for separation, which may cause debonding. Okay, and fourth mode is debonding by concrete crushing. So although this is not directly related to debonding, but concrete crushing can also impact the FRP performance. When concrete crushes due to excessive loading, it affects the bond between the FRP and the substrate. So if there is loss of concrete at the substrate, the bond between the FRP and the substrate can be affected, and it also can cause the debonding. Okay. Now let's see a question now, simple question. Let's try and identify these four modes in the image here. Say here you can see there is a single image, a simply loaded beam which had an FRP strip attached at the surface. Okay, and it was under continuous load. Okay, this was my cracked area and these were my uncracked area. So I have shown you four boxes. These four boxes represent four different types of debonding failure. Okay, you need to identify what each of this box represent, which type of debonding. Okay, so I will wait for a couple of minutes. Try to think what we discussed in the last slide, where you can see different kinds of behavior happening, and try to guess which mode of failure is represented where. Okay, I will mute myself for a couple of minutes. In this time, you can also post your queries in the chat box that I can look at, or just try to solve this question. If you know the answer, post the answers in the chat box also. Okay, so let's see the answers now. Let's see the answers now. So this first one is the mode 1 type of failure that we discussed in the last slide. Okay, what was mode 1? Cut-off cross-section debonding that occurs at the interface, at the end of the plate. So here you can see the FRP plate was ending, and the failure that will occur here is the mode 1 type of debonding failure. Second one, you can see longitudinal cracks that are happening. So this failure will be the mode 2 failure, which is debonding due to flexural cracking that happened in the near the midspan. Because near the midspan, my bending moment will be maximum. So the chances of flexural cracking were maximum here. And you can see the mode 2 type of failure that rose here. Mode 3, the third block represents mode 4. So here you can see concrete crushing happened. So due to concrete crushing, what happened? My FRP bond, the bond between FRP and substrate was affected, and it led to failure of FRP also. So there concrete crushing happened, due to which there was a depression created, and it led to failure of FRP. And finally, this is mode 3, sorry, diagonal shear failure that rose near the supports where shear stress can be critical. Okay, clear with all mode failure and how to identify them? Any doubt in this question? Any doubts to anyone? If no doubts, we'll move ahead. Now, to resist debonding failure, there are three major types of anchorage systems that are used. Okay, what are these? So these are type 1 anchorage system, which is used to prevent and delay interfacial crack opening. So near the joints where cracking starts, how to prevent these types of failure? We use type 1 anchorage. So these includes plate ends where interfacial debonding and cover concrete separation occurs. And here, by simply using a anchorage and nut bolt anchorage system, we can improve the bond strength between the FRP and the substrate. Okay, so here you saw a hole was drilled in which the using which the FRP was screwed with the substrate, which improved the bond. Okay, type 2 is to increase the total available interfacial shear stress shear stress transfer. Okay, this is used to increase the area over which shear stress is transferred, and this is used when the transfer length is less than the effective bond length. So in this image, you can see there was a T beam, okay, and I wanted to do shear strengthening. For this, I used a U strip. However, often we see that the location of maximum shear stress is very near to the end of the T joint. Okay. Now what will happen here? I don't have much FRP. So if my FRP is not enough, what will happen here? Debonding failure can occur. Okay. To ensure that there is no debonding failure, you can see here additional anchorage was done by grooving my FRP into the beam section of the T beam. Okay, the horizontal section of the T beam. Type 3 is to provide shear stress transfer mechanism where no bond length is available beyond critical section. So these generally are found in beam column joint. Okay, so here the critical section of shear stress is located very near to the column. Okay, now in such cases, what will happen if FRP strengthening is not encouraged? This strengthening won't give any sense, because this is the area of maximum shear stress, and here only my FRP is not finding much length. So what is the purpose of FRP then? So that's why here again anchorage systems are used. Okay, by making the use of the vertical member. Okay, now in they to support the different discussed anchorage systems, there are different anchorages devices that can be used. First one is the FRP U jacket. So these are applied on externally bonded FRP to improve the bond performance of a U collar. Okay, as a U collar it is applied. So you can see in the figure, they can be used as a vertically or inclined. So here you can see there was through and through bolting that was done for the FRP strip, and in addition to that, there was a vertical U strip, U jacket FRP was used. Okay, in this image you can see from the side, this was my FRP plate and this was the U wrap that was done to anchor the FRP. Here you can see U wrapping was done on only one side, while here you can see on both side U wrap was used. Here you can see on one side one was used, while on other side two U wraps were used. While here you can see in inclined manner also U wrap FRP U wrap anchors were used. Okay. Second is the metallic anchor system. Okay, so in this, the end of the FRP strip of plate is mechanically anchored using a metal plate cap bolt on both the side of the FRP to the substrate. So this we saw in the previous slide also, using bolting how we do anchoraging. So here you can see in the image, this was my substrate and this was my FRP. To increase the bond between the substrate and the FRP, a mechanical anchorage system was used where a steel plate was metal plate and it was bolted from both the side. Okay, this will improve my bond between the FRP and the substrate, and they are mainly employed near the end of the FRP plate. Okay, so here you can see this, in this diagram, one FRP where mechanical anchorage was not used. This hole is a complete single FRP. So near the end plate, mechanical anchorage system was used, and in between, when the mechanical anchorage system was not used, the failure was in between also and not in the end. So from between the failure occurred and not from the end. So we reduce the chances of type 1 of debonding. Okay. And in this image also you can see several FRP strips were placed on a deck of a slab. Okay, and mechanical anchorage was provided at the end to improve the bond between the FRP and the substrate. Okay. Now, a combination of externally bonded FRP along with mechanical anchors is also commonly used as a combined FRP strengthening system. So, we saw one particular literature earlier today also where such combination gave the maximum strength increment. Okay, in the figure, we can see the same. So, here it's the mechanical fastener bolt. Okay, that was used, mechanical fastener and bolt it was used. So a hole was pre-drilled into the concrete structure, the externally bonded FRP plate was attached in between the holes, and anchor system was installed across the plate. Okay, so this combined is known as HBFRP system. Okay. Another very often used anchor system is FRP anchor system. Okay, FRP anchors. So till now we saw mechanical anchor U strap. These are FRP anchors. So these are made of rolled fiber sheets and bundled of loose fibers. So in the images you can see how these FRP anchors look. So there can be FRP spike anchors, there can be fiber anchors, there can be FRP bolts, there can be FRP dowels. Okay, so what is the mechanism of action of these anchors, FRP anchors? So one end of the anchor, that is dowel part, it it is inserted into the pre-drilled hole in the concrete, and the other end, which is known as the fan, it is epoxied on the FRP strip that is attached externally to the member. Okay, so the end of the fibers are splayed to disperse local stress concentration are known as anchor fibers. Here you can see both the part, that is the dowel part, this part, and this is the anchor fiber. So this part will go inside the concrete through a hole, and this part I will adhere it to the externally bonded FRP sheet by epoxy. So in this image also you can see, so this was my substrate. Okay, here to a hole, I inserted the dowel part and the sheet, and the anchor fan part. Spread it on the FRP sheet. This was my FRP sheet. Okay, and on this I used this FRP anchors to improve the bond. Okay, from the side you can see how it is appearing. This is the embedded length, and these are the fiber fans that are coming on the top and spreading. Okay, and here in this image you can see this can be applied in different types of geometry. Either 90-degree you can drill the hole, or even 45-degree, 60-degree, 135-degree. On both the sides you can do the anchor fans, or either on one side you can use the anchor fan. Okay, so there are different ways in which FRP anchors can be used. And finally, we have pi anchor system. So what do we mean by pi anchors? So these are bonding Pi anchors include bonding a CFRP head plate using two monolithic legs over and through the FRP soffit plate. So my FRP soffit plate is the original FRP plate that I was using for the strengthening, and this kind of assembly where two holes are there on the side and one strip is there at the top. So this combined assembly is known as pi anchor because they appear as a pi, and these are used to improve the bond between the FRP and the substrate, much like we saw earlier, much like we saw in this metallic anchor system. The similar is here. The only difference is this is made of FRP itself, and that was made of a metallic material. Okay. So the Anchorage method we saw till now were mainly for FRP strengthening. Now let's see for FRP used in shear strengthening what all anchorage systems can be used. So we have mechanical faster and mechanical fastened metallic anchor. So in the first image you can see uh, FRP URAP was used, and near the end, metallic anchors were used to improve the bonding and delay the shear failure. Same can be seen in the second image also. FRP U strap with anchor bolts used at the end. Okay. Then there is anchorage through concrete embedment. These are used in places where critical shear plane is very near to the joint and there is not enough surface area available for anchoring. So you can see in the image a hole is drilled in the concrete and that part is used for anchoring the FRP plate. Then FRP spike anchors, the same as we discussed earlier also, pre-drilled hole having dowel neck and the fan part of anchoring, and the fan part that is anchoring the FRP U strip. Okay, the same can be seen in the image also where these were used for near beam column joint strengthening. Then there is patch anchors. So in this, shear cracks are first retrofitted with FRP, and then patching anchors are applied at the top and the bottom of the FRP sheet to improve the bond. And similar can be seen in this image also. There can be a hybrid anchor also where the first FRP is installed, then FRP spike anchors is used, and then patch anchors are applied over the cover. Okay. There can be substrate strengthening. So in this, substrate itself is used to strengthen the bond. So as you can see in the image, there is the concrete substrate over which FRP is placed. Now to improve the bond between the two, a hole is drilled through the FRP and the substrate, and then it is bolted. Okay, so here you can see the hole was drilled, and from the top you can see how it is bolted. This will in turn strengthen the bond. Okay, and finally we have NSM anchors. Okay, so here, which these are very commonly used for anchoring for shear critical region. We saw in the earlier discussion also when we were discussing type 2 and type 3 anchorage. So here the concrete cover is chipped near the critical shear region, and existing FRP is supported using an additional rebar and the grouting material. So you can see here in these assembly how an additional rebar and the grouting material are used to anchor the FRP U strip. Okay, some images like this, here you can see, here you can see, and here you can see different assemblies of NSM anchors. Okay, any doubts in this? Any doubts in the anchorage system part? Why we are doing anchoring? What kind of failure, like debonding is a very critical failure, and to avoid debonding failure we generally opt for anchoring. What are the different types of anchor systems, and how are different anchor devices opted to cover these anchor systems? Mr. Thangamani, you can ask a question. What is your doubt? You raised hand, right? If you are not able to unmute yourself, just write your question in the chat box. I will see in the chat box. Okay. Are you writing or saying? Can you reply? Just post your query in the chat box. I will respond later. Okay, so by this we clear everything about FRP strengthening. From I guess from the fourth or the fifth live session, we started discussing about FRP strengthening. We saw how FRPs are made, what are the different materials used for FRP strengthening. Then we saw different types of FRP that are used for strengthening, how axial strengthening is done, how flexure is done, how shear is done, and mostly when we see we talked about NSM strengthening also, and we talked about beam column joint strengthening also, and we talked that how the debonding type of failure that is very common in FRP strengthening, how they can be reduced by Anchorage system. But now the question is how to decide whether we should opt for FRP strengthening or not, and which material we should choose. That is the question. We understand what is FRP strengthening, how it can be applied to different members, how it can strengthen and how it can fail. But how to choose whether we should go for FRP strengthening or not, and which material we should use. Okay, so these questions play a very critical part in the design of FRP strengthening. Okay, so basically the design is based on the limit state design principle. And what is this limit state design principle? So it has a it sets a acceptable level of safety for serviceability limit. So my serviceability limit is the deflection and the cracking, and the ultimate limits, that is failure, stress, rupture, and fatigue. Okay, so different factors that are considered for design of FRP are divided into three broad categories. Okay, first is the strengthening limit, which is the limited strength criteria of the say, existing structure. This decide whether I can go for FRP strengthening or not. Second is the strength and the serviceability requirement, the strength and the load factor of the structural component. This will help me to choose which FRP material I can use for strengthening. And third is the FRP strength reduction factor. So this helps me to determine how durability, how environmental factor can degrade the FRP, and how I can take the durability performance of a FRP material into account. So if I will consider all these, if I will understand all these three limit, then I can properly design a structure for FRP strengthening. Okay, so let's see each of them one by one in a little discussion. So first is the strengthening limit of existing structure. So what do we mean by strengthening limit? It is imposed to guard the collapse of structure. The existing infrastructure shall possess a minimum required strength so that if FRP fails, the structure doesn't collapse instantaneously. Okay, so we need to make sure that the initial structure before providing strengthening, it should have a certain minimum strength such that if my FRP fails, okay, then my old structure should not collapse completely just at the instance of FRP failure. Okay, that I want to make sure. Why it is important? It is important in terms of its safety. Okay, and how we decide this? By using this relationship. Okay, so, 5 times Rn shall be greater than or equal to 1.1 times SDL plus 0.75 for 1 times SLL. Okay, so here phi is my strength reduction factor, Rn is the nominal strength of the member. Okay, SDL is the dead load, and SLL is the live load effect. Okay, so suppose I have a structure, a three-story building. Okay, and I want to suppose I have a bridge. Okay, reinforced concrete bridge, and I want to strengthen the deck with the FRP. So I first need to check whether my existing bridge, the existing reinforced concrete, is having a minimum strength or not before before going with the FRP strengthening, and that is determined by this equation. So we know what is the dead load acting. So 1.1 times the dead load and 0.75 or 1 times the live load. What to choose between zero point 0.7 and 1? So if my live load are very frequently there on the bridge, then I will choose a factor of 1. If they are not very frequently there on the bridge, then I will choose a factor of 0.75. So if my nominal strength of the member, considering the effect of strength reduction factor like due to durability and environmental factor, If my strength of the member existing structure is more than this value, then only I should go for FRP strengthening. If it is not greater than this value, then it is more suitable to demolish the structure rather than going for strengthening activity. Okay. Now, why this is important? Because FRP is only strengthening the member for flexure or shear or axial. Other possible failure modes like punching shear and bearing capacity of soil, it is not taken into account by FRP. So we need to make sure that our structure itself is capable enough of taking load, and just that additional load that is coming, it is taken by the FRP. Okay. Thus, if a structure fails to possess this minimum sufficient strength, then instead of going for retrofitting, it's better to demolish the structure. Okay, so this will help me to decide whether my structure can be retrofitted or not. Once I've decided whether like FRP can be used or not, the second step is the selection of FRP material based on the strength and the serviceability requirement. So FRP is chosen either for flexure, axial, or shear strengthening. Okay, and the additional effect of improved compressive strength due to flexural FRP use, that like due to confinement, shall not be considered. Okay, the only thing that should be considered is the purpose for which the FRP was used, whether it was used for flexural strengthening or axial strengthening or shear strengthening. Now these requirement of strength and serviceability can be judged by different factors. The first factor is the load consideration, that the chosen FRP shall be capable of withstanding load without undergoing damage. Okay, what are these loads? Dead load, live load, impact load, and fatigue load. So considering all these types of load, my FRP that I'm choosing, it should be able to withstand the load. Second is the environmental conditions. The performance of the FRV should not be affected by the surrounding environment conditions. What are these environment conditions? Thermal expansion, alkalinity, acidity, or electrical conductivity. Due to this, my FRP material should not be affected. And durability consideration. The choice of FRP material should be durable enough to withstand the exposure conditions like hot, dry cycles, freeze thaw cycles, salt water, and UV exposure. This durability consideration part also account for the last step, that is the strength reduction factor, which becomes an important tool when we are estimating the long term performance of FRP. So when we are choosing a FRP system, we need to take into account all these three considerations: the load consideration, the environment consideration, and the durability consideration. So when we talk about load effect, we have seen earlier also how commonly used FRP like carbon, glass, and aramid fiber performs on stress versus strain plot. So glass fiber possesses the maximum strength and strain limit, while the carbon fiber reinforced polymer has the stiffest is the stiffest among the all. Okay. Now on site, there are other types of loading action that can also become critical. Okay, there can be impact loading, creep loading, and fatigue loading. Okay, impact loading, we know sudden load at a point. Creep loading is due to continuous exposure to a sustained load, and fatigue loading is loading unloading cycles that can occur mainly in the bridges. We can see these two types of loading. Okay. Now, under these conditions, this table shows how different FRP performs. So, under impact loading, AFRP's performance is more superior than GFRP and CFRP, while in creep loading, CFRP is more superior than AFRP and GFRP, and in fatigue also, CFRP is more superior than AFRP and GFRP. So, you can see not just the stress versus strain curve, but the performance in other types of loading also becomes a very critical for choosing the right material when we are considering loading effect. Okay. Similarly, we can talk about environmental factors also. So there can be thermal coefficient, conductivity, and alkali acid resistance. So in terms of thermal coefficient, AFRP has the lowest thermal coefficient of expansion, then CFRP, and then GFRP. So GFRP generally matches what are the thermal coefficient of concrete. Okay, it is more compatible with concrete in terms of thermal coefficient. Conductivity, since all of these are not made of metals, still CFRP is more conducted than AFRP and GFRP. Then we have alkali and acid reaction. So in this also CFRP is more superior. It is less prone to damage by alkali and acid compared to AFRP and GFRP. In GFRP, we can see degradation that can happen due to acid or alkali. Okay, and finally, we have durability factors. So, depending upon the exposure condition, different fibers have different reduction factor. So, when we talk about interior exposures, so we see carbon fiber is more superior than aramid fiber and then glass fiber. Glass fiber has the maximum reduction factor. Okay, in case of exterior exposure like bridge piers and in unenclosed parking garages, you can see aramid fiber has better performance than glass fiber. Okay, and carbon fiber has the most superior performance. While in aggressive environments like chemical plants where acid attack can be severe, or in wastewater treatment plant there where there is a lot of hydrosulfuric acid which can be present. So in that also you can see CFRP has more dominant performance compared to AFRP and GFRP. Okay, so you can see in terms of exposure condition, CFRP has the most superior performance while GFRP has the most poor performance. Okay, now just to understand how you can decide a particular FRP if some project is given to you, let's see one case study. So in this case study, you need to decide which material should be chosen for strengthening. So what this study says, so this case study is about strengthening of an aging bridge deck. The background is the bridge deck is a 15-year-old concrete bridge in the coastal city that has been showing signs of deterioration, includes which includes spalling and cracking of the exposure due to exposure of salt water and heavy traffic. The bridge is a crucial transportation link and must remain operational during the strengthening work. As a consultant tasked with choosing the most appropriate FRP material for strengthening the bridge deck, what environmental factors and exposure conditions should you consider, and what impact might these factors have on the choice of FRP materials? On how would you choose the how would you make the choice of the FRP materials? So this is the background given to you in the question about the bridge and the locality of the bridge. Okay, the environment factor and the loading factors also detail. It has been given in this question in the background. Okay, and the question is asked, you are a consultant and you need to take into account what are the different environmental and exposure factors that are critical in for this bridge, and which FRP material you will choose and why. Okay, so I will take a pause for a couple of minutes. Try to reread this question. Try to make a list of which all factors are critical for the structure, and then we'll see the solution. How we can make the choice of a right FRP. Okay, I will unmute myself for a couple of minutes. You can think about this question. By that time, if anyone has any doubt, they can post in the chat box. Okay, so let's see the solution to this case study now. Okay, so we know the background of the bridge deck. Now, based on this background, first is to list down what are the critical factors. So, first critical factor is the coastal region. So, region will come with high humidity, saltwater exposure, and potentially harsh weather conditions. Okay, then we have operation conditions since it is a very busy bridge, so there can be heavy traffic load that was stated in the background. So creep stresses might come into action along with fatigue stresses that also can come into action since there heavy traffic load. Environmental effects can be high temperature in the coastal regions, and the main factors for us here is the flexural strengthening and the shear strengthening. Okay, and other factors that can also come handy is the cost and the availability of the material. Okay, so if we see on the basis of different parameters how different FRP materials perform. So since it is a salt water exposure, so we need our material should be corrosion resistant. So in terms of corrosion resistance, my glass fiber and aramid fiber are better than CFRP. Though CFRP also won't corrode, but still my glass fiber and aramid fibers are better than CFRP in this manner. If I talk about high creep resistance, then my CFRP is better than glass fiber and aramid fiber. If I talk about tensile strength also, my CFRP and AFRP would be better than glass fiber. In deflection control also, since CFRP is very stiff, then it is better than glass fiber and aramid fiber. In terms of thermal performance, we have checked earlier also, glass fiber is more compatible to concrete than CFRP and AFRP. And finally, in terms of cost cap, if I see, my glass fiber is cheaper than AFRP and CFRP. Now, from this slide, you will see there's a lot of confusion. So, what needs to be done? You need to scale each parameter by a certain amount. Like, how much important is each parameter to the like practitioner, to the site, or to the bridge. Okay, once you have done the scaling, like I will rate the tensile strength, like it is 3. I will rate the importance of tensile strength at 5 value, or at the cost cap. I don't have very much constraint about cost. I can go for expensive material also. So my constraint on cost cap will be very low. So based on the constraints, you can go further and make the appropriate choice of material. But for now, based on my judgment, I will choose CFRP. Why? Because it has excellent tensile strength, fatigue resistance, and stiffness. This will help me to take care of heavy traffic load that is coming. Okay, alongside it doesn't corrode also, so it is important in the saltwater exposure environment also. And most importantly, it has proven track record and widespread availability, which will give me a very better understanding about the performance of CFRP. Okay, so this was my view. You can go for AFRP or GFRP also, but you need to give a proper justification and you need to take into account all the factors on your own. Okay, so this is how, knowing what FRP strengthening does, we can decide which type of material we should choose and whether we should go for FRP strengthening or not. Okay, I hope this part is clear to everyone. Any doubt in this question? Okay, let's see the last part for FRP for this session. Now, when we get to site, how to install these FRPs? We have made the choice of FRP and we have taken all the consideration. We have decided the FRP material and we want to now install the FRP. How to install these FRP and what measures should be taken so that FRP is properly installed. So let's discuss that now. Okay, so for installation of FRP on existing infrastructure is a specialized work which requires several steps to be carried out before and after installation of FRP. Now, who decides these several steps? Okay, these several steps are decided by the application guide provided by the manufacturer of FRP. And what are these several steps? So these steps are majorly classified into four categories: the surface preparation of the existing infrastructure, application of FRP, quality check, and repair of FRP after application. Okay, so surface preparation includes measures to ensure adequate bond between FRP and substrate and to ensure proper load transfer. How this is done? By preparation of concrete surface. My surface should be uniform and flat. Checking of tensile strength of surface. This is done by conducting pull off test. Third is addressing environmental conditions like presence of moisture and temperature. Okay, presence of moisture can affect the bonding and temperature can affect the pot light of the FRP. And fourth step in the preparation is the setting out exact location where FRP needs to be installed. Okay, so these four measures are needed for the surface preparation of my existing structure before installation of FRP. Kindly elaborate stepwise how a structure that has been damaged by fire be retrofitted using FRP. Okay, so I will try to add one case study in the next session now. Okay, so we will see one example where how damage has affected a structure and how FRP reinforcement was done for it. So, like that case study will also help us to understand the FRP strengthening at Soul. So probably I will pick this in the next session because right now making a case study like this and then telling a solution will be very complex for me also. So let's see in the next session. We'll take a structure, we'll see due to fire damage what are possible modes of failure that can occur in the structure, what are the critical areas that can be affected, and what we need to do for that. Okay. Mainly, as per my knowledge, due to fire damage, mainly they spalling in concrete because my concrete weakens as my CSH, the main hydration product of concrete, is getting carbonated. So there can be a lot of spalling of cover concrete in case of fire damage. So to repair or retrofit this structure, basic idea can be first you need to seal the cracks. You need to use the shotcreting method so that you can regain the cover, and then if you want to increase the strength you can use for go for flexural strengthening using FRP U strips or plates. Okay, if my majorly flexural strength has been hampered, or if you want to go for shear strengthening, then you can use U strips or horizontal plates on the side. So this is like a very basic overview. Okay, how strengthening can be done. The important point is to identify what is the problem with the structure and what is needed to be taken care of. Okay, I hope it would have given you a basic glimpse of what how structure can be repaired if it is damaged by fire. Okay. Now, coming back to our discussion, in surface preparation, we saw 4 points. There was preparation of concrete surface, checking the tensile strength of substrate, addressing the environmental conditions, and setting out the exact location for where FRP needs to be installed. So let's see these steps one by one. Okay. So preparation of concrete surface includes cleaning of surface. Okay. This includes removing the surface layer of concrete to expose the coarse aggregate and achieve adequate roughness. Using surface preparation methods like open wet grid blasting, water jetting, and sand blasting, we can do this. We need to make sure that the process that we are opting for cleaning, it should not create micro cracking in concrete. It should not damage the concrete. Okay, if it will damage the concrete, it will hamper its strength, which will hamper the ability of it to go for retrofitting. Okay, and third part in cleaning the surface is removing grease, dirt, and oil contamination. Okay, second part that comes in preparation of concrete is sealing the initial cracks. So always before we are going for retrofitting, it is important to seal the cracks that are initially there in the concrete. So if the cracks are identified, okay, if they are distinct cracks, then we can use epoxy or cement mortar grouting injection. If there is corroded reinforcement that are also identified in the concrete in the structure, then cleaning of rebar and applying anti-corrosion measures shall be taken. And if there is surface spalling in the concrete structure, like just I told, when there's fire damage, there can be a lot of surface swelling. So in those cases, first we need to go for micro concreting, shotcreting, or polymer modified mortar application. Once we have prepared the surface, then we should go for retrofitting. Okay. And finally, when preparation of the concrete surface, there we should ensure that the surface is flat. This will avoid any plane out of plane stress buildup. Okay. And it will avoid any type of stress concentration that can occur. Okay. So for avoiding stress concentration, we should make the edges smooth with a corner radius of 50 to 15 to 25 mm. And in critical location with insufficient bond length, we should use anchorages. Okay. So this is how we prepare the concrete surface before application of FRP. Now the second step is to apply the FRP. Okay, the installation of FRP again is divided into several steps. So first is the choice of appropriate material that we can do from the previous step understanding. Then cutting the FRP in desired shape and length, applying a low viscosity epoxy primer on the substrate so that if, my FRP can be bonded properly. Then placing the FRP in desired orientation and pressing to remove any kinds of voids, smoothing so that the surface is smooth, and rolling. Okay, pressing, smoothing, and rolling all are done to remove the entrapped air voids and improve the bonding between FRP and the substrate. Then we can apply a sealer coat of epoxy on the top of the FRP also to enhance the impregnation of fabrics if we are using FRP anchors. Okay, so to improve the anchorage of FRP anchor with the existing FRP strip, we can use our sealer coat of epoxy also. We can apply a saturant coat also to enhance the bonding. And finally, sand pasting is done to make the surface rough and enhance the finishing. Okay, so these are different steps in which FRP is applied on the existing structure. So in this images also you can see installation work has been carried out. So in the first image on the floor T beam, both shear and flexure if strengthening was done. Okay, on the column you can see a FRP confinement material was placed, and in this you can see on shear and flexural strengthening here was done. Here also you can see shear and flexural strengthening. Here you can see FRP confinement. And in this final image, you can see a tank structure was strengthened in multiple direction by a team of skilled laborers. Okay, so this shows you the emphasis of application of FRP. How proper application of FRP can be important. Okay. Once the installation is done, the next step is to check the quality and if there is some repair required after installation. So for quality check, we before application of FRP, we should check the substrate, for which we can do the pull-off testing to ensure that the tensile strength of substrate is sufficient. We can check the adhesion and durability of epoxy. Okay, based on extent of cure, dumbbell test, which is used to check the tensile property, or single shear lap test, which is used to check the adhesion property, and on-site laminate couple test, which is used to verify mixing and wetting of epoxy and fiber. So these all testings are done for the quality of epoxy material. Strength of FRP, that is very common test that we need to do. Okay, quality check for FRP. Thickness, density, fiber orientation, elastic property, ultimate state. These all are very important in case of FRP strengthening. And finally, we have visual inspection. So once my FRP is installed, are there any visual defects? Are there any delamination? Are there any dry voids, air voids, dry spots or bubble that we should check? So if we found any defects like air voids and bubble, we should go for epoxy injection. Okay, as a repair method after FRP application. And if we find any delamination or large affected area on the FRP, we should cut and replace the FRP to ensure that proper FRP strengthening has occurred. Okay. Any doubt in this last part of how FRP is installed on site? Installation of FRP on existing structure. Any doubt in this part? Any doubt in the previous part also, how we decide whether to go for strengthening or not, and how we decide for FRP? So like with the end of this discussion, we are very much clear about complete FRP retrofitting. We started from the choice of material, we came to understanding the material, then we went into how for different types of strengthening flexure, scale, and axial FRP is used. We saw different types of FRP: strip, plate, NSM bar, different areas, column, beam, column joint. And then we talked whether we should how to make choice of FRP material based on the environmental and durability consideration, and how finally we apply a FRP, and after application of FRP how we check the FRP strengthening. Okay, if there are no doubts we can end this session, else I will wait for you for any doubts.
Sir, can you hear me, sir?
Yeah, I can hear you.
Sir, I have a doubt regarding the assignment number 6 regarding last question, that is question number 10. Is there
Okay.
any mistake in the question, sir? Shall I
uh,
know?
can you just let me end this session, then we will see that question. Okay.
Sure, sir, I will wait.
Okay. So I hope there are no doubts in this session right now. So I will conclude the session. So this week we talked about NSM FRP retrofitting, how it functions, what is the role of bond between an NSM and substrate, and a few literature on NSM strengthening. Then we talked about how FRP is used for strengthening of beam column joint and a few literatures to understand factors influencing its performance. Then we discussed about bond failure between FRP and concrete and how different types of anchorage system are used to mitigate them. And finally, we discussed how FRP is applied over concrete, surface preparation and application, and what all design considerations shall be accounted before choosing appropriate FRP for retrofitting activity. Okay, so this was all for today's this live session. If you have any doubts, I am available right now and you can ask me the questions. Thank you.